So much like when we were doing axial load and looking at stress concentrations at places where we had holes or fillets, these kind of changes in area where we have additional stress that needs to be knocked down a peg before we can do our calculations with the stress concentration factor, we have the same concept with torque, right? So we're going to have places of stress concentrations caused by things like couplings or notches, keyholes, or again, just changes in area where maybe you have a shaft that slims down, right? So these are all going to cause stress concentrations, and we're going to use the stress concentration factor along with some more convoluted tables in order to solve these problems. So in this case for torque, our stress concentration relationship is given by the max shear stress is the stress concentration factor times torque C over polar moment of inertia. So it's really the same as the regular shear stress equation, just with this stress concentration factor K added in there. So we can use our tables, look up these values based on the geometry to solve for these circumstances. I will say these circumstances aren't super common, actually. We're not going to be doing this all the time. It's really a lot more of an issue for brittle materials than it is for ductile materials. But I think these are really good to give you some practice looking at kind of annoying graphs and charts to read out, because as you progress on through engineering school, you're going to find that there are a lot of these. There are a lot of things that have been determined by experiment or calculated through geometry, where lots of diagrams and graphs and tables have been given to you, and you just have to know how to use them. So it's a really good opportunity to learn, especially if you haven't taken a class like thermodynamics yet, where you may not have seen lots of graphs and diagrams like this. So it's really just more of a practice in this regard than it is really a focus on stress concentration. Anyways, well, let's look at our table here, right? Let's look at the diagram that we're actually looking at. Here on the left side, you can see an example of this first one is what a coupling would look like, right? So you have these very, very, very common in the real world for piping to be attached with these large couplings. Keyhole notches where you might want to add a gear to your shaft, or just a general change in geometry, kind of this sloping down, this stepped shaft, going from a larger shaft to a smaller shaft. All the things that we would see very commonly in the real world. And then, of course, on the right, we have our fun diagram where we have our stress concentration factor here on the left side, and then our bottom axis is R over D. R being the radius of this step down. So this is looking specifically at this bottom case here. The radius of that step down over the smaller diameter. And then for each of the individual lines here, we're looking at the larger diameter over the smaller diameter. So we'll go ahead and run through a quick example and see what this looks like. So in this example, we've got a built-up shaft designed to rotate at 450 RPM. If the radius of the fillet weld is 13.2 millimeters and the maximum allowable stress is 150 megapascals, determine the power the shaft can transmit. All right, so we know we want to find the power, so we can write out, all right, well, here's our power equation, 2 pi f times torque. They gave us the frequency in the problem, so really the key there is finding the torque. So we can find our torque with that relationship of the shear stress, right? Our shear stress equation. Now, since we have a built-up shaft here, we're going to use that stress concentration factor K is torque times C over J. The first thing I'm going to do, we're going to go ahead and look at that graph and try to figure out what our stress concentration factor K is for this scenario. It's this fillet weld where we're going from 100 millimeters down to 60 millimeters. So let's look again what kind of information I need to pull to line up my values on this chart. So I can see I need R over D, and again that's the radius of the weld over the smaller diameter. So R over D is going to be 13.2. That was given in my problem here. The radius of the fillet weld is 13.2 millimeters over 60. And that gives me 0.22. 0.22. And then the other value that I'm going to need to know which line my 0.22, so my 0.22 comes and it hits, let's see, this is 0.2, 0.21, 0.22. So it hits right here on this line. I just need to figure out which one of these blue lines it touches. So big D over little d, my big diameter over my little diameter is going to be 100 over 60, which is about 1.67. Let's see if we've got a line for that. And we sure do. Here's our 1.67 label. It touches the line that is in the very center. So we've got 5 lines. It is the middle line. So let's see if we can find, where was it, our 0.22. This is 0.21, 0.22. Come up on here and find my center line. My center blue line is this one. It's hitting directly under my mouse right here. So it's hitting right on this line. I come over and just follow it to the left. 1.2. K value of 1.2. So from the table, I got K is 1.2. Perfect. Now let's see, what else do I need? What else do I need to plug in here in order to find my torque? I'm going to go ahead and rearrange this equation. TJ max times, over KC. So my torque, my max shear stress was given as 150 megapascals. Mega is 10 to the 6th. Times my J. My J value is going to come from the smaller shaft here. So pi over 2 times the radius of the smaller shaft. 0.06 to the 4th. All over that K factor, stress concentration factor of 1.2, times the outer radius again of the smaller shaft, 0.06. So that's the important part here. Remember, you're doing this for the smaller shaft here. And once we've got all those, I can plug that into my calculator, and that gives me 42,412 Newton meters. 42,412 Newton meters. And for my very last step here, all I need to do is find the power, right? Determine the power the shaft can transmit. So power equals 2 pi times the frequency, which was 450 RPM. 450 RPM is revolutions per minute. I'm going to go ahead and convert that into seconds here. So 1 minute is 60 seconds. And then multiply by that torque value. And the reason I wanted to convert this into seconds is because a Newton meter per second is a watt, right? It's the SI unit of power, a watt. So I get, when I punch this into my calculator, oh boy, it's a big number, 199.8595 watts, or Newton meter per second. Or you can simplify this, right? You can go ahead and write this as 1.99 megawatts. 1.99 megawatts. Decent bit of power there. So that's it. It's just a matter of looking in the right places to use that chart, right? Learning how that chart works, how we find values from it, and then just plugging it in with our common torsion equations that we've seen.